This is a demonstration of RTK Motion, which is a runtime that SoftImage is selling. At the lowest level, RTK Motion solves character animation in the sense that it does blending, in this example from a walk into a run. You can layer in animations, so I'll have the character look at the camera while she's running. If I were to turn off blending and play these animations piece by piece, you'd see a walk, a run, and the look, you'll notice, effects are only from the waist up. When I turn blending back on, I can have her go from that run to the walk while looking. What's happening is these three activities, the walk, run, and the look, are being layered one on top of the other in a tree of activities. The activities include things like inverse kinematics. If I tell the character to jab or punch at this target and then move it, the animation can be warped using inverse kinematics to hit the target no matter where it is. So inverse kinematics, like playing an animation back like walk or run, is just a standard service that this offers. In this example, we show how a walk through an environment can either be affected or not affected by obstacles that you encounter. In this example, the character doesn't know about the block and therefore walks straight through it. When I turn on inverse kinematics, unlike the boxer that was punching at the target, here the character recognizes an upcoming obstacle, moves his feet to the right place, and then we actually reverse the sense of the IK so that the character is lifted by his feet instead of the other way around. So you can apply that to a complicated terrain. In this case, we've got a woman creeping. We have the character follow the terrain. You can see that she's going up and down the slopes of the hills. If we play the animation back as it came from the motion capture stage, you see that it was actually linear, and so we were playing back with IK having the character's feet follow the ground. In this example, we're going to warp a jump. This flip animation might take up, let's say, 10 units in space, but unfortunately the target, which I want the character to hit here, is, let's say, 33 units away, so when she tries to hit it, she winds up in the wrong place. Instead, we can say warp the 10 unit leap to 11 units, then when you play 3 of them back, you exactly hit it. Here's a set of small animations we have for a character. The character knows how to walk, to grab something, to pose, to stand. And if you look at the grab animation, you see that it's directly in front of the character's waist. If I put that character into an environment and tell it to walk from where it is to pick up this glass, you'll notice a couple of things. One is that it's keeping its eye on the glass. Another is that it smoothly started to walk. It slows to a stop. It bends at the waist to pick up the glass. Remember that the picking up animation was actually in the wrong place. It was at waist level, and so in this example the character is bending at the waist. This is an example of real-time IK being applied to the problem of grasping. So those 4 animations were used to synthesize this entire complicated scene. So look at what's happening. We've got the real-time constraint to keep the eye there. We've got the blending from walk to run, and walk to stand and stand to walk, and so on. We have the IK being applied here, but most importantly we have obstacles in the environment which this character is walking around. If I reset the animation, move a block, and then tell the animation to go, it'll pick a different path. This is an example of what's called path planning, and in truth there are only about 2 lines of code being executed here, one of which is saying plot a path from where you are to where the glass is, and the other of which is, now that you've reached your glass, reach over and pick it up. So we're controlling characters at an extremely high level of abstraction. So if you put a lot of characters into an environment such as a bar and tell them to move around independently, you see that they don't collide with one another, they don't walk through tables. In this case we've got about 4 lines of script per character. They're being told, walk around until you find a seat, sit down. If there's a glass in front of you, then grab the glass, have a drink, and then put it back on the table and get up and find another seat. So about 4 lines of code per character is controlling the entire environment, and you can think how this might be used for, for the starting point, crowds in games, but also because animation can be captured back into XSI, crowds of characters or schools of fish or armies. or leaves blowing in the wind for linear animation as in a film. But because this is so simple to program, you could do pre-visualization with it. You could have a director saying, I want this guy here to walk over there and everybody else get out of his way, for example. Here's another example where I'm controlling the woman character. Everybody else in the scene was generated. They're all getting out of her way. They're all keeping their eye on her. If I tell her to turn around and go back through the room, you'll see that they maintain a distance. They're sort of respectful and don't touch her. These things are easily set up, and then once you have a character that knows how to stay out of another character's way, then that skill can be transferred and reused easily.